All right, welcome back. Got another fun problem here that allows us to have fun and do some work revolving around some factoring, some basic knowledge of logarithms, as well as some basic knowledge of exponents. Can you find x in the equation 64 to the power of x plus 4 to the x equals 222? Hopefully you can. Feel free, if you want, pause the video, try to work it out, and then we can review together and hopefully find that we have each come to the same solution. So first thing is just written the original equation here, rewrite the original equation here at the top in blue. And so first thing, which may or may not be obvious, is that 64 is also a power of 4. And so in order to simplify some of our terms, we can rewrite 64 as an exponent with the base of 4. And so 64 is just going to be rewritten as 4 cubed, since 4 times 4 is 16, times 4 is 64. So now we have 4 cubed to the power of x plus 4 to the x is equal to 222. Now, a quick simple review of some of our exponentiation laws and properties essentially tells us that if you have a quantity raised to an exponent, then raised to an exponent, that the order of exponentiation as it's represented is interchangeable. So 4 to the 3 to the x can be rewritten as 4 to the x to the third. And so this just allows us to rewrite our equation again. And now we can see that we have a common looking term in 4 to the x. So in order to simplify the equation even further, let's just let y arbitrarily let y equal 4x. And plugging back in, we now have y cubed plus y equals 222. Now this equation looks a heck of a lot simpler to deal with and go ahead and solve than the original equation. Next, let's just simply subtract 222 from both sides, so we get 0 on the right hand side and our equation is represented as such. Now, what makes this problem fun and interesting and may not be so intuitive if you're trying to solve this problem is knowing and taking advantage and exploiting the fact that 222 factors down into the product of 6 times 37. It may not seem too relevant, but you'll see in a few steps here how we can exploit that fact to help us solve and find the solution to this equation. So notice that we've got y cubed plus y minus 222. So what if we use one of the factors of 222 to rewrite our y term? And so we can use 37y to rewrite our y term, but in order to maintain a single y, we then have to subtract 36y. So it may look like we've made this equation maybe a little bit more complex, and to some degree we have, but this now allows us to use a form of the equation in which we can manipulate even further and allow us to proceed. Next, let's just take the 37y minus 36y and swap the order. So now we have y cubed minus 36y plus 37y minus 222 equals 0. So once again, we've just taken our original y and rewritten it where 37y less 36y is still y, but now we can have a little bit more fun with this equation, and notably we can factor out a y from the first two terms. So we have y times y squared minus 36, and then we can factor out a 37 from the second two terms. So we now have 37 times y minus 6 on the back half of the left hand side. And you may have noticed that factoring out a y yields a difference of two squares. So y squared minus 36 can be further simplified into y minus 6 times y plus 6. And the second half of the left-hand side still remains the same. And now we've got a common factor of y minus 6 on both the both the first portion of the left side as well as the second portion of the left side. So we can carry on by factoring out y minus 6 from both parts. So this yields y minus 6 times the entire quantity of y times y plus 6 plus 37 equals 0. So now that we've got a product of two quantities times 0, in order to satisfy and solve this equation, one of the two quantities, at least one of the two quantities, has to equal 0. So now we're left with solving the two equations, y minus 6 equals 0, and y times y plus 6 plus 37 equals 0. So obviously first one's pretty simple. We're left with the answer and solution of y equals 6. And second one, we can transform into a quadratic equation and then try to factor it down and solve. Well, this one can't be factored any more cleanly. It's already in its simplest terms, and you'll find that if we plug in and use the quadratic formula, which I'm not going to go through here, you will find that this yields that there are no real roots for y in this case. So in other words, the only potential solution here for y is y equals 6. But you'll also recall that we had let y equals 4 to the power of x, and so combining these two equations now allows us to simplify even further and put down 4 to the power of x equals 6. So let's carry this into a new page. So once again, have the original equation of 64 to the x plus 4 to the x equals 222. And we have simplified this enormously into 4 to the power of x equals 6. Well, now we have the slight problem that we have a variable and an exponent. And so this is where we can use our logarithms to simplify this even further and remove the variable from the exponent. So this just simply becomes the log of base 4 of 6 equals x. Now a quick refresher on some of the laws or properties of logarithms. If we have the log to the base a of b, this can be rewritten as the log of b divided by the log of a. This is commonly referred to as the change of base formula. And you can essentially use any base you want on the right hand side, but we're going to implicitly, or since no base is specified, it's implicitly assumed that we're using base 10, which we are. So now then x is equal to the log of 6 divided by the log of 4. So that actually is our final and precise solution. However, it's not written in a form which may be easily manipulatable or easy to verify and double check and test that our solution works. Since the log of 6 and the log of 4 are both irrational numbers and the decimals move on forever, when we want to convert this to a decimal and to test and verify that our solution works, we're going to lose a little bit of precision. No matter how many decimal points we translate each number to, we can get as close as we want to x, but we will never quite get to x, so to speak. So now we have 0.778, etc., divided by 0.602, etc., is an approximate value of x. And this then lets us see that 1.292, etc., is an approximate value of x. And so once again, if we wanted to get more and more significant, we can just take the log of 6 to 20 decimal points, 30 decimal points, and so forth to allow us to get increasingly as close to x as we would like. So just now we can just take out our calculator and plug in these numbers to double check and verify that this solution works and everything checks out. And so you'll see that we've got 215.99999 plus 5.99999 should approximate 222, which it does to essentially 1/100,000th, 2/100,000ths of 1. And so once again, if we wanted to get to more significant figures, we would just have to expand our approximation or representation of log 6 to more decimal points and so forth. So hopefully, if you tried to work this out, you came up with the same or similar solution. And thanks for watching, and we'll hope to see you back on one of our later videos.